Good morning and good afternoon, wherever you are in the country. I'm personally talking to you from Seattle, Washington, so definitely good morning for me, but good afternoon for those of you in Central and Eastern time. So this is IAQ IQ. Of course, IAQ stands for indoor air quality. That's probably the prerequisite of being in this course today of understanding that abbreviation. This is a one AIA LU HSW approved course. So if you haven't already during your registration, please follow up with your AIA number. We will send a recording of this webinar to all registrants tomorrow. And so if we don't have your AIA number, that'll be a great chance to reply back with it. And we will also verify whether we were able to successfully report your credit to the AIA when we send that tomorrow. So coming from IntelliSafe IAQ, we are a manufacturer of IAQ improving devices, software, and controls. And our guiding principle is to make tomorrow's shared spaces intelligent and safe. And I think that through today's presentation, we'll kind of touch up on that. Of course, today is meant for education, and I would love for you to leave today's course with a strong understanding of why IAQ in shared spaces and facilities and buildings, the importance of it, not just in the wake of the COVID-19 pandemic, but more importantly, in reducing future risk and also improving the well-being of occupants and those that are inhabiting our shared spaces. In addition to that, we will go over some solutions that can be incorporated into new and existing constructions to improve the indoor air quality, with the ultimate goal of creating better air inside than outside, something that may have once been deemed impossible. Now is very much in our grasp, especially when we consider some of what happens outside of our buildings and what we can do and how we can manage and how we can control the inside spaces. So this is me. My name is Dan Litvin. Again, I'm the CMO here at IntelliSafe. My background is in electrical and computer engineering, and the reason I include the rest of the team is that you see a lot of other engineers. So we do come from an engineering background. I talk to engineers all day, every day, and so we will go into the weeds a bit today. We will dive into the depths. So if you have questions, please put them in the Q&A module that's built into Zoom. I will leave time at the end of the talk to address those questions. And then again, you will get a recording, so if some stuff passes over your head, or if I get a little too technical, feel free to phase out for a moment. You can always check it back later and tune in on your own time that way. So let's get started here. So the importance of IAQ, again, indoor air quality. This is a bulletin from the White House website, from the executive branch of our government. And this is the Clean Air in Buildings Pledge, or also known as the Clean Air in Buildings Challenge. This is a nationwide initiative to improve the indoor air quality in our shared spaces, including our schools, our hospitals, our office buildings, not just in our homes. And this is an endeavor that is supported by national groups all over, including EPA, CDC, OSHA, NEOSH, and also on a more international basis as well with the WHO. So this is a major national push right now to ensure that we have this level of cleanliness and safety inside of our shared spaces. And when we look into it, we have some major organizations that are really leading a wonderful charge at providing insight, guidance, regulations, guidelines for what it requires and what it means to have a safe indoor area, including LEED, WELL, Reset, Fitwell, among many, many others. And so the reason I leave this slide here is in your process of working as an architect or as an engineer, as you are digging in and looking to go deeper, of course, please reach out to us at any point. But one of our big concepts and one of our big guiding principles at IntelliSafe IAQ is to ensure and validate. Right? So don't just take our word for it. Here are a few wonderful resources to dive in, to get a scientific explanation and validation of everything that I say during this talk. and to get more information. So going into a few more of these high-level reasons why IAQ is important. So first off, Americans spend around 90% of their time indoors. This is going to be whether it's their commute inside their car or inside of a subway or a train or some sort of public transportation. This is going to be inside of your office space. It's going to be inside of your home. Most of our time is spent inside. Now, indoor air, especially when we don't go and take conscious treatment of the indoor air, tends to be 2 to 5 times of a worse quality than outdoor air. And when we look into some of these numbers, we look into some of the solutions of bringing outdoor into indoor spaces with the idea of purifying indoor air, we have to remember that we have some environmental factors, including pollution, including allergens, including some of the off-gassing from industrial farms, and including wildfire smoke, which is going to prevent indoor air from manifesting and being that high level of quality if all we're doing is taking outdoor air and bringing it inside. Again, I'm here in Seattle from around September until the rains really get started in earnest, sometime in October or even early November. The AQI, the air quality index, is really significantly low due to the wildfire smoke. I actually had a time, I believe it was in September, I opened the door of our balcony. I was just hanging out outside for about 40 seconds, and then my fire alarm went off from the wildfire smoke. So that's just an idea of how bad it can be in parts of the country. And now when we look at things like pandemics, right? This is scientific validation, 47 to 57% chance of another pandemic as deadly and detrimental or worse than the COVID-19 pandemic occurring in the next 25 years. Even before COVID-19, we had people like Bill Gates and some major national organizations saying that this is a matter of time. And if we don't take active steps into mitigating the risk now, then we're just walking into another opportunity for the same thing to repeat itself. You know, we are in a situation where we have a rapidly urbanizing population, right? And that trend is continuing. We had a small break from that during the pandemic, but we're back to it. We inhabit shared spaces, whether it's apartment buildings, office buildings, even our medical facilities. And when we are crammed in so tightly and we don't have a way to purify the air and be proactive about that purification of air, and what I mean by that is trying to get as close to the source of the pathogens, which is us, inside of a space, then we don't have anything that we're effectively doing to reduce the risk. Mask wearing, 6 feet of distance, these are temporary salves during the height of pandemics, not something that, as we are seeing very clearly, that we can maintain going forward and into the long term. And then finally, when we talk about the day-to-day safety and well-being of people, and that is actually probably the major push with this type of technology, even more than the pandemics I just spoke about, we have 50 million plus Americans that suffer from asthma and or allergies. And asthma and allergies are heightened in indoor spaces due to the low quality and oftentimes stagnant air. So just by being able to purify the air and treat those symptoms, we're going to be able to raise the performance, cognitive, physical, mental, emotional, of people inside of our shared spaces, whether we're an employer trying to get the best of our employees, whether we're a medical center trying to provide a healthy place for people to be, or we're an apartment complex, we're building managers looking to be able to provide an edge over our competition and a place where people feel comfortable and safe. This is something that we want to be able to address. And so let's dive into the weeds a little bit. So we talk about IAQ, indoor air quality. We talk about the stuff that's in your air. So what exactly is that stuff? What is lurking in the air that you breathe? So this is going to fall into one of two major categories, either gases or particulate matter. Gases, or as we know, there's 4 states of matter. We have gas, solid, liquid, and if anyone is guessing the 4th, that is plasma. We have nothing to talk about with plasma. We're not going to be talking about blood in this. We're not going to be talking about interstellar occurrences. So let's stick with the three major types of matter here. So gases, liquids, and solids. So in terms of gases, we're going to have three major gases in the air that we breathe. One is going to be our standard gases, things like nitrogen and breathable oxygen, O2. This is the majority of the air that we breathe. The majority of the stuff we're breathing is fortunately safe and or life supportive. I think that we would all struggle mightily living without oxygen. I think we'd only have a couple good minutes of life left if the oxygen was sucked out. But when we talk about IAQ and we talk about what else is in the air, this is where we're going to find harmful gases. Things like CO2, O3, CO. If you're not familiar with the abbreviations of those, you will be in 2 seconds. And then also volatile organic compounds, VOCs. This is going to be a major obstruction inside of our indoor air, mostly due to the fact that this is off-gassed or produced by a lot of the chemicals and processes that we use indoors. So talking about some of these harmful gases. So CO2, carbon dioxide, that's given. We're very familiar with carbon dioxide. Between A, the exhales that we breathe, and B, with the CO2 gas emissions that are causing global warming and climate change. So we're not going to be talking about the ecology of CO2. We're not going to be talking about that side of things. Let's talk about CO2 inside of shared spaces. Two major factors why CO2 might be spiked inside of a space. One is going to be due to pollution outside. CO2 is a byproduct of gas emissions, whether it's from a car or from a factory. But it's also going to be, and more majorly, from the air that we breathe. If we have a lot of people crammed in a small space without good air circulation, CO2 levels are going to rise. When CO2 levels rise, we get drops in performance and well-being. Effects include headaches, dizziness, nausea, drowsiness, sleepiness, increased heart rate. There is an ability to actually have an overdose of CO2, but that is so uncommon that we don't even need to talk about it. But the effects of high levels of CO2 do have a direct effect on our well-being, on our performance, and the way that we feel. Next up is ozone, O3. We know of ozone from the ozone layer, right? And that ozone is going to be very beneficial because it is something that blocks some of the UV rays and other rays that come from the sun, a topic that we'll be talking about later on in this presentation. But ozone on ground level and ozone for us to breathe is going to be detrimental. Ozone does a number on the lungs. Not good for the lungs. There's short-term and long-term detriments from chest pain, shortness of breath, all the way to lung cancer. And ozone is mostly created from two sources, mainly from pollution. And this is a thing that is going to manifest in smog. So something that we see again in urban areas a lot. And you'll notice we talk about urban areas often, and that's going to come into play again when we talk about a modern HVAC system and how bringing outdoor air in isn't always going to be a solution. But just put that as a bookmark. We'll get into that a little bit later. The other place that ozone is going to come is a lot of disinfection technologies, whether it's bipolar ionization, whether it's ozone generators, or even low quality UVC lamps. All those can generate ozone as a byproduct, and ozone should never be used inside of a space that's occupied. If the ozone levels are below the levels that are deemed safe by governmental organizations, ozone is doing, excuse language, but jack shit to go and actually treat anything. But on the other side, if ozone is being used for disinfection, it's going to require levels that are significantly higher than the thresholds that are safe for human breathing. So again, something to be avoided. We can talk more about that later if you have more questions about it. Next up, carbon monoxide, CO, a deadly gas, can cause in low doses fatigue, nausea, headaches, what we've seen before. But again, there is a way to overdose from it, and it's a byproduct of combustion, whether it's gas emission from cars, factories, etc. And finally, two more. We're not going too much into detail with these. Radon, something that you might or might not be familiar with. Radioactive gas comes from natural components in the dirt, can come through cracks, something worth monitoring and investigating. And the nitrogen oxides and sulfur dioxides, these are caused, again, by pollution. They can enter buildings via cracks in the building, whether it's doors or windows. And these have some severe short-term and long-term respiratory damage associated with them. So again, a lot of gases that can be coming in, especially from the outdoor that can be causing damage to the occupants inside of a facility, especially because once the air comes inside from the outdoor source, it oftentimes stagnates inside and it's going to be recycled and added in with the CO2, a really bad cocktail for occupants inside of a facility. All right, and then let's talk about VOCs now, volatile organic compounds, the other gas that's in the air that we need to monitor, that we need to address, that we need to remedy and mitigate as much as is possible. So VOCs come from either products or processes. So they're either inherent to a product. We'll have a list in a moment, but things like the fumes from chemical disinfectants, things like paints that we use are all going to emit VOCs, or they can be created via off-gassing. This can be a chemical process, such as using a bipolar ionization and having some of those ions hit different plastics and materials in a room and separate off and create some of these VOCs inside of the air. So VOCs themselves are associated with a litany of damages and risks. This is actually a very abridged list. ENT, irritation, headaches, nausea, vomiting, dizziness, asthma, respiratory, liver, kidney, central nervous system damage, and cancer. These can be early onset and quick onset, but for the most part, VOCs are going to cause long-term damage. So the detriments might not be seen immediately, but it's something that over repeated long-term exposure can be damaging. And with very clear links, scientific links of the effects of VOCs, to be able to, or to not go and treat and limit the amount of VOCs inside of a space can cause some severe issues later on via lawsuits brought on by building occupants. Fortunately, there's pretty easy ways to go and mitigate VOC risk that isn't using always super green products, even though that's always highly recommended. I know that in existing buildings or with budgets, it's not always accessible. We'll talk about VOC mitigation a little bit later on. These are a list of some VOCs. Not going to go into them. Formaldehyde might be the only one that really rings a bell. Acetone, for those of you that were nail polish, that might ring a bell as well. But on this side, again, you notice that if the names seem to come from a lot of industrial products, that's because that is the tendency there. Now, the way that they come into being, and this part is more important. So we have, again, products or processes. So products, things like paint, varnishes, adhesives, lacquers, right? So common building materials, carpet, vinyl flooring, composite woods, certain upholstery, right? So again, common building materials. One of the recommendations is when you do have new flooring, new furniture, to leave time for it to air out. Unfortunately, off-gassing can happen for a long period of time. So still having ways to limit is going to be important. Some other ways, copiers and printers is an interesting way, interesting note. When those are activated, they do release VOCs. That's the smell that's associated there. And oftentimes odors are VOCs as well. So not all VOCs are bad, for your information. Cooking, so fires, smoking, gas, diesel, industrial emissions, and also air fresheners, cleaning products, and pesticides. So there has been an uptick to poison control calls since beginning of the pandemic due to the vapors of cleaning products, right? And so those are VOCs that are being emitted from cleaning products. So even being careful with the way that we're using some of these industrial disinfectants and seeing if there's ways that we can go and air out a place better or use other technologies that are safer and don't have byproducts to make sure that we're not doing more harm than good while we're disinfecting and treating a space. All right, and so the other side of this whole equation is PM, particulate matter. I mentioned the three states of matter. We talked about gases. Let's talk about liquids and solids. So particulate matter is going to be either tiny little solids or droplets of liquid, which are measured in microns. Micron is a millionth of a meter. And so for that information, a strand of human hair will be about 50 to 70 microns. A grain of table salt is about 330 microns. And the particulate matter that we're talking about is either PM10, which is going to be less than 10 microns, so a fifth to a seventh smaller than the diameter of human hair, or PM 2.5, which is 2.5 microns or smaller. So we're talking about incredibly tiny little pieces of solids or liquids. Now, the danger of these incredibly tiny substances is that when we inhale and breathe in, even if we're breathing properly through our nose, it's going to pass through the hairs in there, it's going to pass down into the throat, and it's going to lodge deeply into the lungs. When we talk about tiny little particulate matter, 2.5, that can get deep, deep, deep into the deep lung. It can even get into the bloodstream via the heart. We talk about PM10, it's going to be a little bit higher on up inside of the lungs. So these are things that cause long-term damage, but can be highly detrimental to the point that the World Health Organization has deemed PM 2.5 with the greatest proportion of adverse health effects related to air pollution. Right. So PM 2.5 especially, and anything that falls in PM 2.5 will technically fall into PM 10, is going to be something that we have to deeply address to reduce the risk of, again, pollution and indoor air quality. Some of the effects related here, again, eye irritation, lung and throat irritation, trouble breathing, decreased lung function, lung cancer, birth defects, heart conditions, aggravated asthma, and all of these effects have been shown to have a greater effect in young children, children about age 5 and younger, the elderly, and those with pre-existing conditions. And so when we look here and we try to figure out where and when we really put in some of this technology, then maybe we go and emphasize first our maternity wards, our senior homes, our daycares, and our preschools for these reasons. And some of the sources of PM, particulate matter, include dust and dirt, pollen and dander, mold spores and allergens, smoke and soot, combustion byproducts, water vapor. And we talk about water vapor because a lot of pathogens and mites will actually travel on little bubbles in the air. That's how COVID-19 was an aerosolized, or is, excuse me, an aerosolized contaminant. And that's one of the reasons why it's so contagious, is that when we talk, it leaves on little bubbles, floats in, and is able to go and travel really quite far and stay alive in that little bubble for days and days. Pathogens, when we talk about them, and I'll use pathogen more or less as a bubble term, so I don't have to say its list all the time, but FYI, viruses, bacteria, fungi, parasites, and mites are all fall into the category of pathogens, agents that can infect and do harm to a living organism. And on that side, just a few notes here. When we talk about the importance of proactive disinfection, right? When we talk about pathogens, a lot of times the initial thought is vaccinations. We roll out widespread vaccinations, and the pathogens don't really do too much harm. Now, this isn't to talk about the rapid evolution and mutation of viruses like we've seen with all the different strains of COVID-19. But in addition to that, we have some major issues that we have to look at. So first, creating a vaccination against a vaccine is incredibly difficult due to the nature of a virus. The COVID-19 vaccination with, whatever level of efficacy it's had really was a miracle of the whole world working together on trying to drive this forward. That is not normally the case. And so trying to limit and avoid the contagion in the first place is going to be the best course of option. And then next, we're talking about viruses right now are the hot button issue again on the wake of the COVID-19 pandemic. But the thing that has been scaring medical professionals much more for a longer period of time is antibiotic resistant bacteria. These can cause severe illness and death without much of a way to treat them, and severe disease spread. I know when we work with medical facilities, even in the height of COVID-19, that was their priority. They're talking about MRSA, they're talking about C. diff, they were talking about these antibacterial resistant bacteria and how to go and mitigate the risk of their spread in the first place. And then just to wrap this up, this is a full term, sick building syndrome. And this is the idea of a full-on syndrome, a series of symptoms of people occupying a space. And there are other ways of working with sick building syndrome. This isn't just improving air quality, but improving air quality is a major element of making places feel safer and improving the well-being, performance, and health of the people inside of spaces. All right. Again, to give a little mental break from that download there, if you have questions at any point, please use the Q&A module. The chat module I will not be monitoring, but the Q&A we will go through and I'll address questions at the end of the talk. All right, so the next question here is we talked about what dirties the air, what lurks in the air. Let's talk about the other side. What defines clean air? Are there parameters that can give us a clear, clean, understandable definition of what is clean air? There are. So there aren't really too many governmental regulations yet. This is something that's in the talks, especially with things like the Clean Air in Buildings Initiative. But we do have the WELL standard does provide some really great outlines. And so this all comes from the WELL building standard. So these are going to be different values. I'm not going to necessarily go into it. You can look at the chart. You can try to mitigate based on the values. But the question that does come from looking at these values is, okay, how do I go and check the building I have and check against these values? How can I know that information? And I know things like CO2 are going to increase while people are inside of a space. I know that with different seasons and different AQI outside, that the air quality might be affected based on the pollution that's occurring outside. So how do I keep tabs of that? And how can I effectively be proactive based on the information I have? And then where that comes in is going to be air quality monitors, right? And so these are devices that you've probably very familiar with. You might have in your homes. You might have already spec'd out for different projects, but are highly important to have on site. These can be as nuanced as having one per space. They can be as broad as having one per wing or even one per floor, depending on the needs of your facility. Again, there are some mandates for carbon monoxide and radon, but not for others. But to have all the information here is going to be important. It's going to be important to have real-time data, so telling what's happening now, and also historic data to be able to understand general trends and to see if mitigation efforts are actually working. There should be clear notifications of when some of these very dangerous products are high inside of your facility, especially when we talk about things like carbon monoxide, which can be lethal in a matter of minutes. And then also something else that you have is the virus index. This is a simulated number. So right now there isn't a good technology out there that you can just put a sensor inside of a building and tell if there are viruses or bacteria inside of your building. Right now, to do that, you're going to need to gather a sample, do lab testing. And so what the viral index is it takes multiple parameters, which are going to be humidity, or relative humidity, temperature, PM 2.5, and carbon dioxide. And based on these four parameters, it's able to take a pretty good guess or estimate at how how many viruses are inside of your space, and B, more importantly, how good of a setting, how viable of a setting is your space for viruses. So having this type of information is going to be very important at mitigating the risk of virus spread in the first place. But we have this, with monitoring, there's one other issue here. And the issue is that, in this graphic, you see PM 2.5 is high. If you have a monitor and PM 2.5 is high, there needs to be something that can actively be done about it to address that level. And this is where using smart technology and building a smart building is going to be important. Now, I know that we don't always have the pleasure or ability to be talking about a brand new facility. We don't always have the ability to build the facility the way that we want it to. And so I'll be talking about some things like HVAC, which is a little bit more difficult to retrofit. And I'll be talking about some technologies that can be incorporated into new and existing facilities. And so I like to think about this section as building a facility's immune system, taking layers to go and make sure that the building is resilient against pathogen, PM, and harmful gases. And so when we talk about HVAC systems, and we're not going to dive into the weeds here, this can be a whole talk, it can be a whole series of talks, and quite honestly, this is something that I am not as qualified as others to speak about. So we're going to go high level in terms of the IAQ improvement side of it. So there are three major things that we want to look at. We want to look at dedicated outdoor air systems, so bringing outdoor air in. We want to be looking at mold management, so we don't have areas inside the building which are creating those allergens for the people inside. And we want to be looking at proper filtration, which is going to limit the effects of being able to not do numbers 1 or 2 as well as we would like to. So let's talk about dedicated outdoor air systems. So a dedicated outdoor air system is the idea of bringing new air inside of a building. If it's cold outside, to treat it and warm it up first. If it's hot outside, to cool it and then bring it inside of a space. The idea is that outdoor air, with all the natural checks and balances and all the space for air to travel and move, should be cleaner than stagnated indoor air between all the off-gassing, CO2, etc. But one of the major issues that we look at, and the reason I have this smoggy city image, is where are we drawing our outdoor air from? If we're in a city that does suffer from smog, let's say we're in downtown LA, or we're in one of our Asian cities that are notoriously right now dealing with smog issues, then bringing that air inside is going to oftentimes do more harm than good. This is also going to be something, again, wildfire season, right? If it is, you're in Seattle, you're in Portland, you're in San Francisco, or the surrounding area, and there's wildfires raging, to be bringing that air in won't do anything good for the people inside. Then we also need to make sure that proper air exchanges are delivered, that we have enough new novel air being passed through the facility so that we don't raise those levels again of CO2, etc. And then we have other factors to look at: the noise, the cost. So inside, ideally, this is going to be a great thing to do, but we need to be able to make sure that we're doing it in a safe and beneficial way. Something else that is going to be needing the ability to incorporate is going to be able to run full or partial air flushes. This is a full exchange or partial exchange of air. Definitely recommended for new constructions at the end of the construction to run for about 14 days. Constant full air flushes for the off-gassing. But also there's going to be times where, whether it's a pandemic breakout, new furniture being brought in, flooring done, painting redone, the ability to have an air flush inside of a space. And then also too, want to make sure that we have what's called a direct source of ventilation. So this is going to limit the ability to cross-contaminate between spaces. So especially on the return feed, as the air is passing back into the main AHU, that we don't have some of the VOCs from the copier room passing into other spaces. So we don't have the germs from the nurse's office or from Phil's office and Phil's not feeling too well, those germs to be passing into all the neighboring offices. So again, getting that good quality outdoor air is going to be important. One of the best things that we can do, but it's not always going to be the best thing or the only thing. Next up, mold management. So we have in facilities, there are opportunities for mold to develop, whether we have leaks in facilities, whether we have gaps or holes, or we have condensation building on the pipes, in the HVAC unit, wherever it might be. If we have mold inside a facility, then those mold spores can be detached, they can float around and trigger asthma and allergy attacks against the people inside the space. So we want to mitigate that and manage that. And so one of the ways we can do that is incorporating UVC light on the AHUs, on the coils, and the collection bins as well, to go and make sure that the biofilm is constantly disinfected. This is not only going to provide remediation of mold, it's going to provide a small degree of germicidal effect, and it's also going to increase the lifespan of the HVAC unit, of the air handling unit, because of a lower pressure system. It allows it to function optimally for a longer period of time. We also are going to want to make sure that proper filtration is in place. This proper filtration is going to help with some of the smoke, soot, and poor quality outdoor air that we just spoke about, and is going to help with some of the detached mold spores or whatever we might see that we just mentioned. And so then we talk about filtration. What is filtration? Well, filtration is going to fall into two major categories. We have our HEPA and MERV filters. We can talk about these as our PM filters. And then we have our active carbon filters. We can think about our active carbon filters as our VOC filters. When we combine the two together, we're going to be able to take VOCs, we're going to be able to take our PM matter, still in this equation, some of our harmful gases and some of our pathogens aren't fully equated for, but we still have solutions for those. So hang on, we'll talk about ways we can mitigate those in a few moments. But let's first dive into these two types of filters. So HEPA and MERV. So a MERV 17 filter equals a HEPA filter, just different types of filtration. When we look at a HEPA or a MERV 17 filter, we see right here PM1 to PM3. So it's going to be our larger aspect of PM 2.5. We're getting above a 99% reduction. That's going to be a 2, 3, 4 log reduction that we're looking at there. Same idea for our larger particulates. And we're even getting from 0.3 to 1 microns, close to a 4 log reduction. That's actually highly significant. When we talk about the aerosolized particulates that COVID-19 floats on, this is actually going to catch most of the bubbles that it's on. Unfortunately, some of the virus can still get through, and that is incredibly small. It'll still not be affected. But when we talk about what else we can do, having just the virus is going to be much easier to work with. So highly effective at getting these larger particulates out of the air. And this is the reason why this type of technology was first developed for nuclear power plants and the exactitude they needed there. NASA rockets, this is literally rocket science and the exactitude they need there, and for hospitals to avoid and limit contagions and infections. Now, another thing that we'll have to look at when we are dealing with filters is the CADR, the clean air delivery rate. This is going to be based on the size and grade of the filter, and this means how much air is able to pass through it. The clean air delivery rate needs to be equivalent with whatever unit it's working with, whether it's an air purifier standalone or it's an HVAC system. And then it's also going to be something that we need to look at to understand how often these filters need to be replaced. Typical HEPA or MERV filter has a 3 to 12 month lifespan, depending on, again, the CADR, depending on the air quality passing through it. And then one last little note, pro tip here. You notice right here, it's about true HEPA. Unfortunately, there's a lot of cheeky marketing that's out there, and you'll see sometimes HEPA-like or HEPA-type filter. That is not the same as a true HEPA or absolute HEPA. If you want that MERV 17 rating, make sure that you have that type of language. If it's a HEPA type or HEPA-like, they just have a form that looks like a HEPA filter, but it's probably acting somewhere more in this orange or yellowish range than this green range here that we can expect from a true HEPA. Oops. Wrong way. And then on the other side, active carbon filtration, also known as using activated charcoal filtration. And so what this type of filter does is it's able to draw in VOCs via a process called adsorption. This is essentially trapping the VOCs and gluing it to the filter. And so we want a wider carbon filter that's going to provide more surface area for the VOCs to be caught on. But these filters are really effective at mitigating VOCs. That's why I said before, we have off-gas and we have all these different effects. There are simple ways to mitigate VOCs. This is the way to incorporate active carbon filtration in multiple sites inside of a facility, and especially where there is higher risk for off-gassing. 6 to 12-month lifespan, depending on application, just like the HEPA filter. Oftentimes, they're used in conjunction, which so long as the cadder and the pressure system inside of whatever fan is blowing allows it, they do make a really good 1-2 punch working together. But as mentioned previously, neither HEPA or MERV HEPA, MERV, or active carbon disinfects against pathogens. While the HEPA, yes, will limit some of the pathogens that are able to get through it, will catch some of the mold spores, will catch some of the aerosolized pathogens, will catch some of the larger bacteria, mites, and parasites. It's not actively being able to treat the pathogens. It's also not really able to do much for the CO2 or ozone inside of a space. Fortunately, there's one more technology here that needs to be talked about and known, which can address that, and that technology is UVC light. UVC is part of the electromagnetic spectrum. It is from around 100 to 400 nanometers. It is, actually, ultraviolet light is. UVC is part of that bandwidth. It typically gets filtered out by the ozone layer and some of the layers in our stratosphere and atmosphere. But when we create it on Earth, we're able to have a potently germicidal effect due to UVC's ability to scramble the DNA and RNA of incredibly small pathogens. That's why if we're able to run things through a HEPA filter, get less dust, get less things in the way, and just treat with UVC, we're able to reduce a 3, 4, 5, 6 log 99.9999% reduction of a lot of our viruses and bacteria in a matter of seconds. So 250 to 280 nanometer is a commonly used wavelength, or set of wavelength, bandwidth of wavelengths. 254 nanometer you may have heard of. That's because the technology right now, low pressure mercury, is what's most readily available and most affordable. And this is something that is time tested. It's been used for, at this point, more than 100 years for this purpose. And we also have a newer technology. It's been around for about 25 years, but it's really coming onto its own over the past 5-10 years, called far UVC, which mitigates the major concern from 250 to 280 nanometers, which is the safety of direct occupation and direct exposure. We'll talk more about that in literally a few moments. So let's continue on. So UVC disinfection, and this is going to be utilizing UVC light, again, in the wavelength of about 100 to 280 nanometer, the whole bandwidth. So we get inactivation of pathogens. We're able to disassemble certain gases, including carbon dioxide, ozone, and some VOCs into their constituent parts. So for example, 2 molecules of ozone, 2 O3s, will become 3 O2s, and O2 is the breathable oxygen that we need to survive. We're able to get, as we mentioned before, the air handling improvements via biofilm reductions. Also, when we're talking about using what we call whole room UVC or upper air UVC, we're getting really wide volumes of air coverage. When we talk about some sort of blower, we only have that localized air that naturally has convection currents moving in. When we talk about UV, we're getting a really wide and proactive way of reaching out. And on that side, we're able to get some level of surface disinfection using UVC disinfection as well. And so talking about typical UVC, again, from the 250 to 280 range, a few considerations. So one, dosage. Dosage equals UVC intensity times time. And different pathogens need different dosages for effective treatment. And so when we have things passing through, for example, an air handling unit at a very fast rate, we need very high intensities of UVC. There's also here, if we have a smaller particle, a smaller virus, a smaller bacteria, so therefore, what's left after the HEPA filtration, those are going to require much smaller dosage than something like a big, thick mold spore with a very thick protein wall outside of it. The concept of near versus far air. So the closer we are to the source of pathogens or pollution inside of a facility, the more effectively we can go and treat it. So using this type of technology more localized to where people are inside of a space, inside of a classroom, inside of an office, we're able to address the need more effectively than if it's removed all the way to the air handling unit, which is shared across the facility and has a lot of opportunity for cross-contamination. And then there's different effects and exposure limits at different wavelengths. So not all UVC is made equal. So for example, UVC at the wavelength of around 185, something you might see if you perchance the Wild West of Amazon.com is going to create ozone as a byproduct. We've already talked about the dangers of ozone and how we do not ever want that in an occupied area. And quite honestly, unless we know exactly what we're doing, we never really want it inside of our facility to begin with. You need at least about 2 hours of good air flushing until that area is safe for entry again. There's going to be 222 or around that wavelength, far UVC, we'll talk about in a moment, which is actually safe for direct exposure. But when we talk about that 254 nanometer, there are exposure limits set by the ACGIH, which right now are around 6 millijoules per centimeter squared over an 8-hour period. Which is essentially saying it's fine if you're under it for a little bit, but it's not something that we ever want to actively have direct exposure to. So it's a little safety threshold, but it's not a technology that's meant to be on while people are inside of a space. It could be on inside of a chamber. So for example, if you had an air purifier that was assisted by UVC, great thing to have. But if you have whole room UVC at 254 nanometers with a bunch of students in there, not a great thing to have. But what is great to have is far UVC. So far UVC is a technology, again, I don't want to say emerging technology. It sounds like it's brand new. It's been researched for about 20, 25 years, a lot of amazing results, and they have researched to very extremely high dosages on human and all sorts of mammalian skin and eyes, and there has been no damage associated. The wavelength cannot penetrate through the layer of skin or through the lens of the eye. No damage, no noticeable effects of it. But on the other side, when we talk about pathogens, it has another effect. In addition to the DNA and RNA scrambling, it also can go and break up protein walls inside of pathogens. Therefore, for a lot of gram-positive, meaning having a protein wall outside of the bacteria, or a lot of viruses that are held together by their protein, the disinfection happens a lot quicker than just 254. And again, this is something that can be used in occupied spaces. That means that we're able to have this light working and treating as we're inside of a space and talking. So we're able to proactively almost reach out and disinfect, battle, and put away some of these harmful pathogens inside of these occupied spaces. This is why this technology, I call it, and so a lot of people are really calling it the future of disinfection technology. Between the safety and its efficacy, it really does have the promise of making much safer spaces when we're talking about just on the level of pathogens. Last part here is no harmful byproducts are associated here. So there's no ozone generation, there's no off-gassing, creating VOCs or anything like that. So again, a really amazing technology to incorporate inside of our shared spaces. So how can we maximize efficacy? We just learned about a bunch of different technologies. Is there a way to incorporate it all together? And there is. So we have 4 components here. With incorporating a modern HVAC system, we talked about that already with bringing the outdoor air in. We're not going to talk more about it here. We have next localized IAQ technology, working that near air front, trying to provide disinfection of pathogens, reduction of PM, reduction of harmful gases, reduction of VOCs, right close to the source, right close to the most important part of the facility, which is the people. We have responsive monitoring, so providing the data and applying that data to the system to make sure that the system is addressing the real-time needs. And finally, taking a building as a living, breathing organism, building its immunity, and allowing direct occupant engagement with this living entity that is the building, so that people not only feel well physically, but feel more confident and feel protected mentally and even emotionally from the technology that's inside of a building. So let's go and explore these 3 briefly here. So we look at localized IAQ technology. We can incorporate all of these technologies together, right? So we can combine the air purification, combine HEPA filtration, remove the PM, combine UVC 254 nanometer light, affordable, very readily available and safe inside closed containers to go and reduce the pathogens, reduce the CO2, reduce the ozone, reduce some VOCs, and then for whatever VOCs get through, active carbon to go and create radically improved air quality indoors. We can incorporate 222 nanometer UVC with this as well to go and proactively reach out, to proactively reduce some of those VOCs, to proactively reduce the bacteria, viruses, mold spores that are in the air and close to the mouths of the people that are inside of the space. And what we can do is we can take the actual data that's occurring inside of the space, see what we have. Do we have high PM? Do we have high VOCs? Do we have high CO2? And we can take the entire building to respond to it. We can signal that data to the HVAC system to make sure that it's blowing a little more fresh air into that part of the building. We can talk about the internal air purification of these IAQ devices inside of the space to go and create a little bit of a higher internal blowing of their internal fan system to go and purify the air. And then when baseline levels have been reached, whether the space is empty for the night, whether the technology is working well, run everything into eco mode. Have more of a green solution here. Don't run up bills any more than they need to. And let buildings be smarter. We are in the 21st century. We have the technology. It's time to actually apply that in smart ways with our buildings. And then the last part here is client engagement, right? Let clients see what active parts building owners are doing for them. Let clients and let facility managers and let people get involved and know and see historically what's been done. Let them learn about the technology that's been that's included there, and let this be a real movement, right? Again, we have the Safer Buildings Challenge occurring right now. This is a way that we can go and move that challenge forward and use, let's say, peer support to go and raise the importance of this issue and to go and make sure that everyone is aware and knows the best way. Because you can also, through this occupant engagement, also provide information of, hey, it's flu season. Hey, we have COVID-19 happening right now. We're asking for 6 feet of separation during this time. And from there, you'll get a lot more buy-in from people if they know that they're being met halfway with their facility managers and owners. And just as we end this talk right here, just a quick one slide on a school system that has been applying this. Right, this is a New Jersey school. They're able to upgrade their existing HVAC system. They apply germicidal UVC to go and mitigate the mold. It's an old school, about 30, 40 years old. They weren't able to fully upgrade their HVAC system, but they're able to take proactive steps. They incorporated technology, the clean air technology inside of all their classrooms, their cafeterias, their computer rooms to go and mitigate the VOCs, the PM, the gases, the pathogens. In this case, they used external UVC at 254 nanometers that they're able to run during unoccupied times to do their best of flushing out the air without the actual ability to do that. From there, there's basic monitoring services that tells the staff, and that's provides parents the understanding of what kind of air quality is inside their school and how they're keeping their students safe, and staff training to understand the best way of understanding the system and operating the system. So it's nothing out of the reach. This is nothing, today's conversation isn't anything in terms of, let's say, theoretical, but this is all doable, actionable technology, and things that we can do to mitigate risk. And I think that a goal that we should have as technologists, as architects, as building designers, as occupants of buildings, is to see how close we can get to making indoor air safer and healthier than outdoor air. And in many instances, that can be and should be the standard. All right, also, again, my name is Dan Lipton. Thank you so much for attending today. If you have any questions, feel free to reach out to us. That's our office phone line. You can go to our website and reach out to us that way. We'll get back to you tomorrow with a recording of this webinar, and we'll let you know if you've been successfully reported to the AIA for attending. If you haven't been, we'll ask for your AIA number. And what we'll do now is open up for some Q&A. So again, if you want to stick around, you're more than welcome to. If you want to head out, again, thanks so much for coming, and looking forward to connecting with you again in the future for a future webinar.